I chose to use computational fluid dynamics to model fluid flow through a jet pump. And this was just something that I was interested in, and yeah, so there are many different applications for jet pumps. Many of them are in the oil and gas industry, as far as like frac water recovery, and then also another big one is in a volatile environment where like an electric pump could create a spark and cause a subsequent explosion, which wouldn't be good. And then also they can be used when when the fluid that they're pumping could damage a mechanical pump. And so basically just the principle that they work on is really fascinating to me, and using like the Venturi effect and stuff. And so the efficiency of these pumps is really important, because basic idea is to get as much fluid flow through the pump as easily as possible. And so I chose to focus on looking at different geometries of the jet pump and seeing how that affected the efficiency of the pump. And so yeah, I created a couple of different models in Fluent, and used that piece of software to model the fluid flow through them. And yeah, so basically Fluent uses the momentum equations and also the energy equations based on the Navier-Stokes parts of the equations. And so the fluid that I chose to model with this was an compressible fluid, basically water, because that's like the most common fluid that would be put through these pumps. And so in Fluent, I chose to use a K epsilon turbulence model, and then also a coupled solver, because that kind of created the best results and everything to come up with the most realistic model. And then also in Fluent, I selected the jet inlet to be a velocity inlet, and then the pump inlet to be a pressure inlet. And so this allows the jet to push fluid through the pump and then out the outlet in the pressure velocity. Okay, these are the initial geometries that I used, and I just put these together for a quick baseline comparison that I could throw into Fluent and basically get a control flow through the jet pump. And so basically I did that and came up with these numbers, and so the control got 46 for the flow, and then I decided to half the mixing tube length and then have the divergent tube length and then have the diameter of the mixing tube. And I did each one of these one by one on their own, so we could just get a basic quick comparison of each one. And so as you can see, having the diameter of the mixing tube had the most overall effect on the flow through the tube. And just some quick speculation about this, I'm guessing was probably because it's got more, the smaller diameter is more restrictive, and then there's also more influences from the wall friction factors and kind of some things like that. Alright, so now we got a quick little wrap-up conclusion here. I feel like this is a really good project. I learned a lot about using Fluent and taking an idea that I had on paper and creating a whole geometry and mesh and everything, and throwing it into Fluent and performing some fluid analysis on it. And so this is just a quick result of that. It's a pressure profile on the walls of the jet pump, and you can see there's low pressure on the intake and high pressure on the outlet, so fluid can just kind of follow the pressure and cruise right through there. And then here's some velocity streamlines so you can see how fluid moves through the pump. And then this final picture is the velocity gradients going through the jet pump, and you can see there's high velocity that kind of mixes and diverges out with the entire flow. And so like overall, you know, this is a really cool project. I'd love to do a little bit of further research and maybe check out like the different geometries on the intake, and so like a kind of a cone here versus just a flat wall, and I think that would be really interesting. Overall, this is a great project, and I felt like I learned a lot about Fluent and all the kind of fluid dynamics and stuff that kind of goes into that and everything.